Welcome to Algoresh. Today we're going to talk about a concept that's so fundamental it pretty much dictates how nearly every single database on the planet is built. So let's start with a question that sounds really simple, but the answer is anything but. When you save a file, where does it actually go? We like to think of our data living in the cloud or, in a folder on our desktop, but that's just a nice abstraction. The truth is, data has a physical home, and that home has some very strict rules. Right, so that physical world is governed by what we can call the laws of hardware. If you really want to understand why databases work the way they do, you first have to understand the actual physical metal they run on. Okay, let's dive right in by looking at the two main kinds of storage drives. On one side, you've got the classic hard disk drive, the HDD. Just picture a tiny, super fast record player. It has these spinning magnetic platters and a little mechanical arm that has to physically race back and forth to find your data. And on the other side, you've got the modern solid-state drive, or SSD. It's a totally different beast, no moving parts at all, just a grid of electronic memory cells. Now, they seem like they're from different planets, right? Mechanical versus electronic. But here's the thing. They both share a fundamental principle that changes absolutely everything for software. Inside an SSD, those little memory cells are organized into groups called pages. And then those pages are grouped into even bigger chunks called blocks. You can't just reach in and read or write a single byte of data. The hardware forces you to work with these fixed-size chunks. And this is the key. It's not just SSDs. The old spinning disks work the same way. For an HDD, making that little arm seek to a random spot is an eternity in computer time. For an SSD, it's just really inefficient. And this gives us the golden rules of storage. First, accessing random tiny bits of data is painfully slow. Second, the most expensive part of any data operation is just finding the right spot. And third, reading or writing a whole continuous block of data is ridiculously fast and cheap. So what's the takeaway? For software to be fast, it absolutely must think in blocks, just like the hardware does. And this brings us right to the central challenge for any database. How in the world do you find a needle in a digital haystack? Think about it. If your file has billions of entries, you can't just scan the whole thing every time you need one record. That would be unbelievably slow. The answer is to use an index. It's just like the index at the back of a textbook. It's a totally separate little structure that tells you exactly where to go to find what you're looking for, without having to read every single page. But here's the catch. Not just any index will do. It has to be designed from the ground up specifically for that block-based storage we just talked about. And this is where one of the most important, most elegant data structures in all of computer science makes its grand entrance. Enter the B tree. This thing is the quiet workhorse behind most databases you've ever used. Its defining feature, its superpower, is its shape. It's designed to be extremely short but incredibly wide. And the reason for that very specific shape is the key to all of its power. So why short and wide? Well, you probably guessed it. It all comes back to the hardware. Let's think about that disk block again. Whether it's on an HDD or an SSD, just think of it as a fixed-size container, like one page in a book. A database always reads and writes data one of these pages at a time. And here is the absolute genius of the B tree. Its nodes are engineered to fit perfectly inside one of those disk blocks. One node of the tree fits into one block on the disk. This means that to read a node, the database only has to do one single disk read. And because that node is so wide, it can hold pointers to thousands of other nodes below it. Let's just walk through how this creates such incredible efficiency. To find one single record among billions, you start at the top, the root node. That's one disk read. That node points you to the correct child in the next level down. That's a second disk read. You repeat this just a couple more times, and bam, you found your data. Because the tree is so wide, it's also incredibly shallow. You can navigate a tree with a billion items in just 4 or 5 steps. 4 or 5 disk reads. That is astonishingly fast, and it's all because the software was designed to speak the language of the hardware. This is the fundamental takeaway. Hardware shapes software. So you see, the B tree isn't just some abstract algorithm from a computer science class. It's a direct, ingenious answer to the real-world physical constraints of our storage devices. Building software that works this closely with disks isn't easy. There are a lot of details and pitfalls, but the payoff in performance is absolutely immense. This deep connection between hardware and software is what makes our modern data systems possible, but it also leaves us with a fascinating question. New technologies like non-volatile memory are coming out that don't operate in blocks. They're byte addressable, much more like RAM. So as this kind of hardware becomes more common, the fundamental rules of the game are going to change. And when the hardware changes, what do you think the data